Hey guys, welcome back to another video on the Digital Logic series. Today we are going to be looking at another problem from the textbook related to 1's and 2's complements. So in binary, there are primarily two methods to represent negative numbers. This is the 1's complement and the 2's complement. So with the 1's complement, computing a negative number is fairly simple. You just perform a not operation, and this is essentially flipping all the zeros to ones and all the ones to zeros. However, with the 2's complement, we take the 1's complement of the number and then we increment that number by 1. So we'll get into examples in a moment, and I won't go into too much detail about the difference between the 1's and 2's complement, but essentially it's how they handle the number 0. So the 1's complement has two representations of 0, this being 0, 0, 0, 0 if you're using a 4-bit string, and that will represent positive 0. And however, we can also represent negative 0 by using 1, 1, 1, 1. If we look at the 2's complement, it only has one representation of 0, this being 0, 0, 0, 0. If you're more interested on the theory behind the 1's and 2's complement, there's a lot of resources online. I recommend you check those out. But for today, we're going to focus strictly on the example from the textbook. So first up, problem A asks us to find the 1's and 2's complement for three 8-bit binary strings. Like I mentioned previously, to find the 1's complement, we're going to perform a not operation, and we're going to change every 0 to a 1 and every 1 to a 0. So starting off, we will change this 0's to 1's and 1's to 0's. And just like that, part 1 is finished. These are the 1's complements. Now going to the 2's complement, we will just increment the 1's complement by 1, and then that will be our final answer. And that is our final answer for 2's complements. Now for problem B, we're given the exact same three binary strings, but this time we're told that they are already in signed 2's complement format, and we need to find their decimal values. So the first two numbers are positive, and we know this by looking at the leftmost bit being 0. We see that that number is 0 as well as this one. The difference for this last string is that it's 1, so we know it's negative, and this will be constant amongst any type of string of binary numbers that you're converting. So we can start off with the first one, use the standard positional weights, and add up the numbers. So this will be 2 to the 0th power, 2 to the 1st power, 2 to the 2nd, 2 to the 3rd, 2 to the 4th, 2 to the 5th. So we're going to be looking at these here because that's where a 1 is present. So the final answer will be 1 multiplied by 2 to the 0th power plus 1 multiplied by 2 to the 4th power plus 1 multiplied by 2 to the 5th power. This will get us 1 plus 16 plus 32 with a final answer of positive 49. Next up, we'll be looking at the second part, which will follow the exact same process as the first part. And again, we'll only be looking at these numbers because anywhere it's 0, the answer will be 0. So the math will come out to 1 multiplied by 2 to the 2nd plus 1 multiplied by 2 to the 4th plus 1 multiplied by 2 to the 5th. This will get us 4 plus 16 plus 32, with a final answer of positive 52. And then for the final part, as I mentioned previously, we know this is negative by looking at that leftmost bit. And when a number is negative, what we need to do is take the 2's complement. So we'll start off by taking the 1's complement, which is inversing all the numbers. So 1's become 0's and 0's become 1. And then doing that next part, which is incrementing it by 1. And then this now is in the signed 2's complement, and we will use the standard positional weights like we did with the previous two. So writing out the math. This will get us 95. However, we know that it's negative, so all we have to do is stick a negative sign in the front, and that is our final answer. Finally, problem C asks for the decimal value of B6 in hexadecimal form using an unsigned number system. Since it's unsigned, we don't care about the signed bits. We just apply the standard base 16 positional weights. So rewriting the number out, B6, we know that B corresponds to a position of 11 because A is 10, B is 11. And then 6 just remains as 6. So what we do is multiply 6 by 16 to the 0th power, and then B by 16 to the 1st power. This ends up becoming 6 multiplied by 16 to the 0 plus 11 multiplied by 16 to the 1st power. This ends up getting 6 plus 176, with a final number of 182, with a subscript of 10 to show that that is in decimal form. That's all for this video on 1's and 2's complements for binary numbers. Thank you for watching, and if you have any questions on these examples or suggestions for a specific problem that you want to see next, leave that in the comments below, and make sure to check out other videos on the channel if you need any additional help. See you in the next one.